Okay, yeah, because I gotta record a class so people who cannot come can watch the lecture. All right, so you can see here is our lab setting for today. There will be a big board outside. We're going to lay down on the board later. And there will be a weight scale here to record the FS. So typically, basically, we're just going to get the height of your center of mass from your toe to your center of mass. So that's a distance from a toe to your center of mass. That's what we want to know today. Okay, so why is it? Okay. So the topic today is center of gravity. And what is center of gravity? Or where is the center of gravity of this box? Anybody knows it? Have you ever heard of this word, center of gravity? Probably high school physics. Okay, but the memory is really not there. Okay, hi. So we just finished our introduction, but yeah, we can talk individually later. Yeah. And do you mind to introduce yourself to us?
I'm Caroline.
Caroline. Okay. Cool. Yeah. So I think everybody's here. So that will be our typical lab setting with these people. Okay. So center of gravity means there's a point in this box that can represent this whole mass and obeys a rule of physics. So in this box, we can consider there are multiple small masses, small point of mass, like the red dot, right? But if we want to calculate all the red dots, that'll be very hard. They require a lot of computation. So someone's really smart. They develop a concept called center of gravity or center of mass that we can use a single point of mass to represent the physics of this object. Right, so, and usually say in a balance point, so it's in the middle for this box. And the center of mass will obey the physics rules, like if you apply F, a force to this box, and the whole motion will obey F equals to ma, the second Newton's law. All right, so that's a concept of center of mass with a easy object. But for today, we need the center of mass of our body. So think about it. Where should our center of mass be? It's in a balance point, right? So if we consider in the midline, it should be a line on the midline, right? And we typically have some more mass at our lower body. So it'll be a little bit below our middle line. So it'll be cross this line and a bit lower. So it'll be umbilicus around it. Yeah. So in this graph, the center of mass of this human is here. And if the center of mass is exceeding the margin of support, like exceeding the foot, then he'll probably fall down. That's a physics. Okay. So that really simplifies the question of human movement. We just need to calculate the point, not the whole body or each segment of your body. And the second question comes, like, can you change your center of gravity? Initially, we thought it's like around in the middle of your body, right? Can you change it? Can you make it higher or lower? Think about this one. We need to consider an object with multiple point of mass, right? And then we combine those to be one point. But say if this red dot go up a little bit, it becomes here. Will the center of mass change? Yes, right? The center of mass would change upward a little bit, right? Okay, so same thing in our body. Like currently, my center of mass is here. What if I raise my arm? The center of mass will go up a little bit, right? Yeah, so actually we can change our center of gravity just by raising our arms. And we'll prove it later. So that's why we have this lab. We'll prove that our center of mass will move upward a little bit after we raise our arms. Good? Okay. And the third question, can your center of mass or center of gravity be outside of your body? Is it possible? Yeah, someone's nodding their head. Can you give us an example?
I mean, if you're like kind of doing like a yoga pose,
Yeah, exactly.
Because there's weight over here and there's weight over here. It might not be on your body.
Yeah, that's pretty smart. So we got an excellent example here. Like this position, your center of mass should be crossing this line, right? When I hold him like this. So the center of gravity will be aligned here. And also if I hold him like this, the center of gravity will be aligned with this gravity line. So the center of mass is typically here when you're in this position. So you can change your center of mass and also you can make it outside of your body. Sounds pretty cool, right? Yeah, at least for me, it's pretty cool. So that's today's setting. And so we'll lie down on the board. We'll use a weight scale to record the force on this end. And then we want to calculate the distance from your toe to your center of mass. When your arms are by your sides, and then we're going to raise our arms and see if the center of mass changes. Okay, but how do we calculate the distance from your toe to the center of mass? We need a concept called moment. Have you heard of moment previously, or torque? Yeah? And how do we calculate a moment in this situation? Here is an axis of rotation, and we apply a force here. What's moment to this segment? How do we calculate moment? We need force times the distance from the force to axis of rotation. So I'll draw something here, and yeah. Just a second. Why? What's happening? Sorry, there's some technical issue. Probably have a lot of this semester. But yeah, hopefully you can see my writing. And the first concept is moment. Can you see it? No. Yeah, I hope the resolution is good enough for people who's gonna watch that. So first concept is moment. We know force, right? We know force. When there's a box, we apply force to it, it'll move, right? Okay, but moment is usually be used in angular movement. So here's an axis of rotation, and here is a stick. If we apply force to that stick, what will happen to that stick? It'll rotate, right? Around the axis of rotation. We want to know how much force is applying to this kind of rotation movement. So that's basically torque or moment. So we will say moment equals to force, but that's in angular movement. And force is usually used in linear movement. So moment is a force in angular movement. We can think about it that way. Okay, so how do we calculate moment? The same example, here is an axis of rotation, and here is a stick. And if we want to move that stick, would it be easier if I apply force here, or I apply force here? which way would be easier for you to move that stick? Think about when you're opening a door. Would you gonna push a door on the end or in the middle of the door? At the end. Yeah. Okay, that's the answer. Right. So think about this thing. I want to move it upwards, and it's gonna rotate around my finger. I want to move it here, or I want to move it here. I want to move it at the end, right? That's easier. What means easier? Easier means we need less force. But why do we need less force? Because there's more distance here. So we want to move that stick, means we want to have the same moment to move that stick. And the moment equals to force times the distance. So if the distance is higher, then we don't need that much force. We can have less force. So that's the concept of moment. Equals to force times the distance from force to axis of rotation. So if you got longer distance, you don't need that much force. Okay, make sense? Okay. So that's a concept we need today. But the setting would be the big board here. And here will be the axis of rotation. And there will be a weight scale here. Weight scale. Okay, so if there's board only, and we know the board's center of mass is in the middle, and the board, the weight of the board is W. What would be the number showing on the weight scale? Would be the same as the weight of the board, or would it be larger or less? It's a little bit hard to think, right? So we need to calculate it. And if the board is not moving, right? It's not rotating. So the total moment is the same, it's 0. So we know total moment is 0. And there are two directions of the moment. One is clockwise, the other is counterclockwise, right? So the board will bring the weight of the board will bring it this way. That'll be clockwise, right? But there's another force applied by the weight scale. So that force will make this board rotate this way, counterclockwise. And because those two moments are equal to each other, so the board is not moving, because the net moment is 0. Okay, so how do we calculate the moment created by the board? And now it'll be force times distance, right? So assume the length of the board is L. The mass of the board will create a torque called W times 1/2L, right? That's the distance here, 1/2L. Can you see that? Hopefully. Okay, make sense? So that's a total clockwise torque in this system. And that's from the mass of the board. But why isn't the board moving? Because there is another weight scale here, right? Supporting the board. And that weight scale should create the same torque, same amplitude of torque, but different direction, right? So the mass of the board will create this torque that will be clockwise. And the weight scale will have a force here recorded. And the torque created by that force will be F times what? The distance from force to axis of rotation. So that'll be L, right? F times L. And those two should be equal to each other. So again, clockwise torque should be the same as counterclockwise torque. And clockwise torque here is created by the mass of the board, right? And how do we calculate the moment created by the mass of the board? That'll be weight times 1/2L, right? Because 1/2L is the distance from axis of rotation to center of mass. That'll be force times distance, the moment equation. I'll write it here. Force times distance. Make sense? And also counterclockwise torque here. The force applied by this weight scale, this direction, so that'll be force times L, the total distance. And what can we conclude from here? We can see there are L's here, right? And L's here. So we can remove it, right? Because we divide by L in both sides, so that'll disappear. And what we found, 1/2W equals to F. What is F? F is a weight scale reading, right? And the weight scale reading would be half of the mass of the board. Make sense? So if the board weighs, if the board weighs 100 kilogram, what will be the force reading here? Will be 50 or 200? We'll put in the equation here, right? 100 kg is here, 100 kg times 1/2 equals to F, right? So F is the scale reading. That'll be 1/2 times 100, that'll be 50. So again, there is a board, here is fixed, that says axis of rotation. And if we put a force scale here, the scale reading will be half of the mass of the board. Make sense? A little bit hard. So if you want to solve this question, that's a typical process. You find all the force, you find all the direction of the moment. And if it's not moving, clockwise torque should be the same as counterclockwise torque. Yeah, torque is moment, sorry. Kind of use it interchangeable, but make sure it's not confusing to you. So let me know if you feel confused. Okay? Okay. So right now, the system will be a little bit harder because there will be a guy lying on there. And think about it. If a person is lying on the board, which direction of moment will be created? Would he add some clockwise torque, or would he add some counterclockwise torque? If there is no, I think about it, if you lie on the board, would the weight scale be higher or lower? It should be higher, right? It should be higher, right? But why is it higher? Think about the system. The force is creating counterclockwise torque, right? And it's used to compensate the moment created by this guy. So the people will create a force here that will be clockwise, and a force will be counterclockwise. So if you add some clockwise moment to the system, you need some more counterclockwise moment to compensate it. Okay, make sense? I'm sorry your eyes are a little bit confused, but yeah, that's typical. Don't worry about it. You'll figure out later. So we'll do a free body diagram again, but this time with somebody lying on the board. So again, here's axis of rotation. We put a big board here, and the length of the board will be L. We put a force scale here, that'll record a force from this end. So there'll probably be a force. And also, the board has its own mass, right? Let's say it's W board. And then somebody is going to lie down on the board. And his center of mass will be probably here. Okay. And his body weight will be weight of body weight. I would say just BW. Easier. Weight of board and body weight. And for today's lab, we want to figure out how far is it from your center of mass to your toe, or from your center of mass to the axis of rotation. Right? So that's what we want to figure out. We call it C. Okay, so that's all the force in the system, right? The body weight of this person, the weight of the board, and also the force from the recording here. So there are 3 forces, so there should be 3 moments. Again, and the board is not rotating, right? So the total moment should be 0. Make sense? Okay, so let's list all the clockwise torque first. So all the clockwise torque. Who are creating clockwise torque? The person, right? The person is creating clockwise torque. The force is this way, and the rotator board this way, right? And how do we calculate the torque or the moment by that person? Let's say it'll be body weight times what? Times distance, right? Times distance. Force times distance. Body weight times C. The distance from center of mass to axis of rotation. So that's one of the clockwise torque. Is there any other there? This one is also clockwise torque, right? So we plus it, plus. And force will be W times distance will be 1/2L. So that's all the clockwise torque we have in this system. Cool? Makes sense. Okay. What about counterclockwise torque? Who's creating counterclockwise torque? Which force? Or this one? Right. Right. Yes, because this force will make this board rotate this way, right? So that's counterclockwise torque. How do we calculate the torque? Force times distance. So it'll be F times what? Times L. Right, times L. The distance from force to the axis of rotation, that'll be L. Okay, makes sense? And what's next? We know clockwise torque is the same as counterclockwise torque, right? So these 2 equations should be the same. Then we can listen here. BW times C plus W times 1/2L equals to force times L. The equation would look like that. And why do we need that equation? What's the purpose for today's lab? We want to figure out how far is it from your center of mass to your toe, right? So what's the parameter there? That will be C, right? We want to figure out C. How do we figure it out? We're going to do some magic. So it'll be BW times C equals to F times L minus W times 1/2L. We just move this thing that way on that side, right? So that's the first step. And then we divide everything by body weight. So that'll be divide by body weight, and here we also divide by body weight. So now you got C. Make sense? Feel a little bit sleepy? Okay. Any questions? Or want me to derive it again? Okay, so we'll do that the same thing later. It'll be 5 minutes later. And if you figure out some question, we can discuss about it later. Okay, so that's the equation we need today. And the concept, we use moment or torque. It's the same thing. Moment or torque is calculated by force times distance from force to axis of rotation. And we know in this system, it's not rotating. So clockwise moment should be the same as counterclockwise moment. So then we list all the clockwise moment and all the counterclockwise moment. And those people are equal to each other. Then we got C, finally. And everything is based on the concept of center of mass, because we think the board is a point of mass. Your human body is a point of mass. Right? So we were based on that concept. Okay. All right, so let's go back to so that's a typical process when we, this one knows. All right, so that's a typical process when we solve a problem. Is a board rotating? It's not, right? So it's not, because total moment equals to 0. What does that mean if total moment equals to 0? It means clockwise moment is equal to counterclockwise moment, right? Just a second, and to make sure I recorded the right thing. Okay, cool. Sorry about that. So again, total moment is 0, means clockwise moment equals to counterclockwise moment. Then you list all the clockwise moment and all the counterclockwise moment, and to derive the equation based on that. Okay. So we've done the free body diagram time. That's called a free body diagram. So based on what we have right now, that's everything you need for today's lab. You need the mass of the board, right? So you can put it here, W. And also you need the length of the board, which is L in our free body diagram. You need the length of the board and also the mass of the board. And we're going to measure it later. And you need your body mass here and your height. So if you don't know your body mass or height, we gotta scale backwards, because we're gonna record your mass and height later if you need it. And also, we're going to put a 4 scale here, and the scale reading of board only, and your arms by the side and your arms overhead. Okay, so that's all the number you need for today's lab to solve the problem. Yeah, makes sense. And it's all based on this equation. So we got several steps. The first step is like we got a weight scale over there. So if you don't know your height or body weight, you can acquire it at the there. And when somebody's figuring out their weight, you can finish question 1 to 4 on the manual. Yeah, that's basically the same thing that we just done. Yeah, but I want you to write it again, to consolidate the memory, your brain. Yeah, so step 1, you can get your weight, and others finish question 1 to 4. And be careful that body weight is confidential information, so don't try to look at others' body weight. And then step 2, we're going to put a scale beneath one side of the board, record the reading, and then everybody will lie on the board and record the reading, with arms by side and arms overhead. That's the second step. And yeah, and third step. And then you're going to enter all your information to a Google Sheet. And the Google Sheet is on Canvas. So here's Canvas, and that's a lab assignment today. And you should be able to get the spreadsheet here. They'll look like this, right? So you're going to enter your body mass, your height, and a scale reading when arms by side and arms overhead. And this column is for female, and this column is for male. Yeah, and we separate female and male because that's part of the assignment, and this arrangement will make data analysis easier. All right. Okay, so I think that's for now. Any questions? Yeah, cool. So we're going to finish question 1 to 4 on your manual. And if you don't know your height and weight, you can get it at the end of the classroom.